Now we are ready to start processing these data. You saw in the animation that there is all this background signal, which makes it difficult to isolate the cell bodies. So the goal of this video is to try to identify and remove that background blur. And we're going to do this using a pretty naive image processing algorithm. And the way that I'm going to go about that is by assuming that the background blur has a very low spatial frequency characteristic, whereas the cell bodies have a high spatial frequency characteristic. So that means that the blur, I'm assuming that the blur is large and spread out, whereas the soma, the cell bodies that we want to identify, are local and have sharper edges. Now, as I also mentioned a few videos ago, it's questionable whether this background blur is really noise per se, because a lot of this background actually is coming from neurons, is coming from neuropil. But for the purposes of identifying the cell bodies here, this background signal actually is noise that we want to remove. Okay, so here you see the workflow. So we create an average image. This is the average over all the time points, all the image frames. And then we are going to blur this average image to estimate the background signal, which looks like this. And then when subtracting the background from the average image, that's going to give us this image here. And I think you can agree that it's now much easier to visually identify all the soma, all the cell bodies here, compared to this original image. Finally, this image over here shows the data binarized, which means I've converted this image from having a range of pixel values to having only two values, 0 and 1, or you can think of it as being false or true. And this is the binarized image that we are going to use to identify all of the neurons, to isolate all these cell bodies. So that's the identification comes up in the next video. But for now, we're going to work through this procedure here. So as with previous videos, this is now your chance to pause the video, switch to MATLAB, and work through the partially completed MATLAB file. And now I'm going to switch to MATLAB and walk you through my solution. Okay, so looking ahead, you can see that I've broken this down into multiple steps. So we have step 1, which is actually in 2 sub-steps, and then step 2, step 3. Here we're going to pause to do a little bit of visualization, and then the final step is going to be thresholding the image. Okay, so let's go back and start with step 1. So we want to compute the average map. So that's actually not so difficult. We have our data matrix here called data. So we say mean data. Now we have to think carefully about what we want to compute the mean over, which dimension we want to take the average over. So it's not the first dimension, that's the rows of the image. It's not the second dimension, that's the columns. Of course, it is the third dimension. So we want to compute the average over the third dimension. And it's a good idea to check out the size of this variable. So I'll write whose av map to confirm that this actually is an image. And in fact, we can also make an image of this image. So I'll write image sc av map. Just a little bit of sanity checking to make sure that we are not making any coding mistakes already right up in the beginning. Okay, so then we want to normalize this map to a range of 0 to 1. Now, image normalization is sometimes necessary and sometimes useful. In this case, we are going to normalize the image to facilitate identifying a threshold, and that's coming later. So what we want to do is normalize this data to a range that's called min-max scaling in statistics. Okay, so this is done by 2 steps. First, we subtract the smallest value in the matrix, and then we divide by the largest value in the matrix. So I'm going to replace avmap by avmap minus the smallest value, which is the MATLAB function min. Now, when we just have min avmap like this, because this is a matrix, the result of this function, the output of min, is actually going to give me an entire list of values. And that's because when you input a matrix into the min function, MATLAB is going to compute the minimum value for each column separately. So we get 455 minimum values corresponding to the smallest value from each column. But this is not what we want. We want the minimum value over the entire matrix, over the entire map. So there's several ways that you could get the global minimum. One way is to vectorize the map. So I write open parenthesis, colon, close parenthesis, and this is vectorizing the map. So this is transforming this from a matrix into a single vector. And that means that the min function is actually only seeing a single vector or one long list of numbers. So we get one minimum value. Okay, notice also that I'm overriding the variable avmat. So that means that I'm actually changing the variable avmat, so we no longer have access to the original scale of the data, which is fine in this case, but it's just something to be aware of. Okay, so that was the first step here. Subtract the smallest value. Now we need to divide by the largest value. So again, we write avmat divided by, now of course we want max. Now you could use the same formatting, so to vectorize this matrix as I do here. I'm going to show you a slightly different way. I'm going to write all. So just like this. So this now tells MATLAB that we want to compute the maximum value over the entirety of the matrix. Okay, so these, you could use this method or this method. Those are basically equivalent. Okay, so then let's see, I'll run this line of code. Now we can see we can make an image of this. Now this average map is going to look visually exactly the same as the original average map. And that's because we haven't really changed any of the values locally. All we've done is scale the color. So we can see that by adding a color bar that it goes from 0 up to 1. Very nice. Okay, so the next thing that we want to do is apply MATLAB's local adaptive histogram equalization. And this basically helps make the image a little bit more homogeneous over space. So we input the matrix that we want to compute, or that we want to apply the adaptive histogram equalization to. And I actually want to show this again. So color map hot. So here you see what the original matrix looks like. And now I'm going to apply this adaptive histogram equalization and then look at it again. So now you see it's a little bit brighter. The contrast over space is a little bit more normalized. So that means we can already better isolate the individual cell bodies here. Okay, so then we have step 2, and that is to estimate the background. Actually, let me close this figure. Estimate the background as a fuzzy version of the image. So I'm going to use this function im for image, Gauss for Gaussian, and filt for filter. So this is going to return a version of the input image, which is avmap, that is filtered with a Gaussian, so a two-dimensional Gaussian filter. Okay, so let's run this line and let's see what this background, the estimate of our background activity looks like. Well, it doesn't really look like the image that I showed in these slides. Now, the issue here is that the default width of the Gaussian is a little bit small. So we can try adding a second input into this function. For example, let's try, how about 40? Okay, so let's try running this again and recreate this image. And now, this is a little bit too blurry, I think. This is a little too much. I would like to have I want to have a little bit more detail. So I want to use a narrower Gaussian. So I spent a little bit of time playing around with some different parameters, and I found that a value of 10 works pretty well. So a Gaussian width of 10 pixels provides a reasonably good estimate of the background, and that you see here. Again, I'll change the color map to be hot. So now you see, and this actually looks like what I showed in the slides a few moments ago. Okay, so this is our background activity. Now we are going to create, I call this the boosted SNR map, but it's actually just literally the difference between the foreground, the average map and the background. So we say avmap minus background, and now we still have another important step to do, step 4, but we are going to take a moment to visualize what we have done so far. Okay, so I create a new figure. I'm already at the top. Right when I open up this figure, I'm setting the color map to be hot. Okay, so now what do we do here? Well, this is one long line of text, and it's actually 4 separate lines of code. So we're creating a subplot geometry, and then we are producing an image. We're plotting an image into the first of 4 subplots. So this is going to be 2 rows and 2 columns. And then I'm setting the axis to be square, and I'm setting the title to be mean. So MATLAB is happy enough to run all of these 4 separate lines of code, even though they come, these are 4 separate MATLAB commands, although they are in one line of text. And MATLAB knows how to separate them because they are the commas. You could also use semicolons here. But I want to take a moment here to discuss MATLAB coding style. Now, it's not always a good idea to have multiple MATLAB commands on the same line of text. The reason is that it can make your text more dense and difficult to parse, and therefore also difficult to debug and difficult for other people to understand. However, something like this actually can be useful. For example, if you have multiple lines of code where you are only making some small change. So let's say we have 4 images that all look really similar, so they would be just on different subplots, and maybe this would be called avmap 1, 2, 3, 4. So in this case, this is actually facilitating coding by having 4 lines of text that are nearly identical with a few small changes, and this provides a pretty compact way to add, to have many MATLAB commands in a relatively small amount of space. Anyway, I just wanted to mention this as a coding style issue. Okay, so I'm going to leave this long line of code like this, make sure that still works. And now you can see, these other parts of the code where we are showing images. I've separated these commands into separate lines of code. Okay, so here we have the average map, the mean map. Here in the second subplot, so this is 2 by 2 geometry. This is the first subplot. This is the second subplot over here. And we are going to plot the background, so the estimate of the blur, and the title is giving us a MATLAB error. Okay, this is not a valid way of writing titles. So this actually needs to be a string or a character array. So I'm going to use 2 single quotes here, and let's call this the background signal. All right, very nice. Then we have the foreground image, and that's going to go in the third subplot, which is located over here. So there we see an image, and now it's kind of hard to really understand what's going on here, and that's because of the color limit that MATLAB automatically chose. So to see this, we can write color bar to activate the color bar. So now the range of these values goes from around -0.3 to +0.6. So it's an asymmetric color map, and yeah, it's a little difficult to interpret. So we are going to find a good color limit via trial and error. So we know that this map has color values that range from 0 to 1, and so does this one. And then we subtract these two, and that gives us the possibility for negative numbers. But negative numbers in this map here mean that the background signal was stronger than the average. So I'm going to start the color map at 0 to say that we don't really care about negative values in here. Negative values in this image basically just means that there was stronger blur. Okay, so we can try something like 0 to 1, and that's a little bit better, but you can see it's a little dim. So let's try, this is something you can discover on your own empirically. I'm going to go with a value of 0.3. I think this nicely illustrates the individual cell bodies much better than here. Okay, so now I'm actually going to redraw this just to get rid of the color bar over here. Okay, very nice. So this was like our little pause to visualize what we've done so far. The next step, or the final step here, is going to be to threshold the foreground map. So what we want to do is pick a threshold that we are going to apply to this image over here. And the idea of the thresholding is that we want to have a Boolean map, or a logical map, where all of the pixel values are either 0 or 1, corresponding to false and true, and those are going to be used to identify the individual cell bodies. So we want all of the non-cell bodies to be false and all the cell bodies to have a value of true. So let me just show you what this line is going to look like. Here we're going to say, I forget what I called this. This is called foreground. So variable foreground greater than thresh val. So that's how we are going to create this thresholded image. So now the question is, how do we create a threshold, a numerical value? How do we pick a numerical value based on this image? Well, the way that I'm going to recommend doing this is by starting off by changing the color limits of this image and use the color limits to set our threshold. So right now, the threshold, the lower threshold would be 0 when we see this. But if you look carefully, I don't know if you can see this on the video, but you can certainly see it on your MATLAB screen. We still get a little bit of red fluff. In fact, maybe I will reduce this to be, how about 0.2, just so it's a little bit more visible. So you still see there's a lot of pixels that have values greater than 0. So I don't think 0 is going to be a good threshold. Instead, let's try a threshold of 0.1. So now the idea is that anything that's black in this image is going to be left out of the thresholded image. Now, 0.1 seems to be too stringent because we removed a lot of cell bodies. So again, this is something that I spent a few minutes playing around with, and I came up with a threshold of 0.05. I think this finds a relatively good balance that allows us to isolate the cell bodies without getting too much false positives from the residual background activity. Okay, so here I will write that the thresh val is 0.05. Then we can run these two lines of code, and then we can visualize that. Of course, the that here is referring to this thresholded image that's going to go in the fourth subplot. All right, very nice. So here was our fairly naive image processing based method of preparing the image data in order to isolate individual cell bodies. Now, we haven't yet isolated the cell bodies, and you can also see that there's, some of these balls here, these circles, these clearly correspond to cell bodies. We still get a little bit of fluff here. There's still a little bit of flotsam and jetsam, these little tiny specks from artifacts or neuropil that are out of the focus. So in the next video, we're going to clean up this binarized thresholded image a little bit more and then identify pixels corresponding to unique cell bodies.